In this recording, I'm going to go over all of the different experiments that we did in our chemical reaction lab with the 6 different stations, so that if you're absent or if you need to revisit them in order to be able to fix or finish your observations, then hopefully these will help. Make sure when you are observing these reactions that you cover the before, during, and after of the reaction like I have structured on our answer document. And make sure you're using your senses. I know because it's a video, you're really just limited to what you see and hear, but that makes those details extra important. We need to focus on what's changing, what's new, what our senses are telling us, not just narrating what I do. I know what I've already done or what the instructions in the lab told us to do. What I want you to focus on is color, size, shape, texture of the stuff that we're starting with and of what we're ending with, to help tell the full story of what's happening and how our chemicals are changing in our chemical reaction. So, for example, if I have a test tube with an acid in it, I want you to tell me that the acid is a light pink transparent liquid, not just there is acid in the test tube, or she put the acid into the test tube. I also want to take a quick look at our answer document to touch on a couple of things to make sure that you can get full credit for all of this work that you're going to be doing. So here on our answer document, notice how I gave you these pre-formatted subscripts as well as the arrow and plus signs. These are all things that we need to be using in our chemical equations when we are writing out and balancing our chemical equations. When we write things out, if we have subscripts or any numbers basically in a chemical formula, should be subscripts. And it's only when we are balancing our chemical equations that we might need a full-size number in front of that substance. But you would never end up putting any kind of coefficient or full-size number inside a substance or a formula to balance it, because we can't break up or balance the individual elements of a compound separately. We can only balance them by putting numbers in the spaces in front of those compounds. Our types of reactions are just our single replacement, double replacement, synthesis, decomposition, combustion. So just make sure you type those out there. It's going to be part of your process in finding the balanced equations, because I'm not going to be giving you a spelled out chemical equation. You're going to have to pay attention to the substances that I'm using in these videos, as well as the instructions that pop up before each video in order to put together what are these substances that are being mixed together. Those are going to be your reactants, stuff you put before the arrow, and then use your knowledge about what type of equation that is going to be, what type of reaction it is, in order to predict those products, just like as if it was one of those problems in our packet on pages 11 through 14 that we've been predicting products on. If you need help with that, come in for help. These videos are just to help make sure that you can get started on your own, take care of all of those observations, and then if you need help figuring out what to do or how to do this, then please come in and talk to me about it so that you can understand it, instead of just turning it in and not understanding it and not getting full credit here or on your test when you've got to do this. I do want to point out that in our stations 4 and 5, the during and after are combined instead of being separate. That's because these are kind of too fast or too slow, and they don't really have a specific kind of end point that's as clear as some of the other ones. So I said in the instructions that you could combine them, and that's why I've already done that here for you. Please don't do that in any other reactions. Even if you think it's boring, there is important stuff for you to be noting that's different in that during and after part. So I need you to make those specific observations there. Here we've got our reactants for our first reaction, aluminum and copper 2 chloride. And I've gone ahead and I've put a little piece of aluminum in our test tube. I'm going to add some copper chloride to it. And now we're going to bring this over and hold this into the flame just to get this reaction started. There we go. Here at station number 2, we have some ethanol. And I'm just gonna put some on our lab table and ignite it for you. Now that the reaction is done, there's no more fire. Notice there is some stuff left behind on the table. It smears around. It's liquid, but that liquidy stuff isn't flammable liquid that just got left behind. So make sure you make a note about seeing that liquid that was left behind on the table, and if you write your reaction out, you might also be able to figure out and tell me what that liquid is that's left behind on our table. So here's our piece of steel wool already in our evaporating dish. Give you a little bit of an angle on it to be able to see. I have already fluffed this up a little bit, so I've separated some of these fibers, just making sure that they've got some space between them, some air between them. And steel wool is steel. It's not wool. It just looks like wool and feels like wool. It's kind of fluffy and a little bit softer than you normally think of steel being. And for this reaction, keep in mind that steel is 99.9% iron. And the other stuff that's in there doesn't really matter. So this is pure iron here in this steel wool. And all we need to do to get this iron reacting is touch it lightly with a battery. Battery is not part of the actual reaction, just gives it the energy to get going there. finally it stopped. I was kind of expecting that it would come over here. You can kind of see some of the original iron left over. It's just a slightly different color than the rest of this. You might see more if I flip it over. Yeah. I flip it so you can see that contrast, kind of a before-after look all together here. And then just because it's so much fun, I am going to go ahead and touch this to that part. I do not get a reaction going. There's a little bit of unreacted stuff there. But just touching this to the stuff that's already reacted doesn't really get anything going. Can't react twice. Once this reaction has happened, it's done. So here at this station, we have some potassium iodide and lead nitrate. They look pretty similar, but I'll give you some views there, the simple before part of our reactants. And then we're going to fill this about halfway up, potassium iodide. And then we are going to add a few drops of this lead nitrate. Now I can pull this out. So it is still kind of liquidy. You can see it's not actually a solid frozen chunk like ice is, but we have definitely had a chemical reaction happen here. All right, here at station number 5, we've got some copper chloride solution here that I've already poured into a little evaporating dish where we're going to be doing our reaction. You might be able to see it better in there than in the Erlenmeyer flask anyway. And the only other thing that we're going to be doing to this is putting these little electrodes into this solution. There's 2 of them. And then watching it react. And I mentioned in the instructions that this graphite that I'm using at the end of these electrodes that I've got clamped into these wire clips is inert. It's all made out of carbon and it is not going to react with the copper chloride. It's just going to help get the electricity from this battery into that solution. If I'd stuck that battery into the evaporating dish like what we did with our steel wool earlier, then the battery would get all wet and rusty and it'd actually become part of this reaction. So all this fancy stuff I'm doing with these wires and these electrodes is actually just to keep from having other stuff involved in this reaction. So let's go ahead and zoom in because this is going to be kind of subtle here. So we're going to have to focus on what happens at each of these electrodes in this solution. Now this will keep reacting, but I wanted to pull these out, give you a little bit of a closer look at this electrode. In the copper chloride, it looks a little different than it does out of it. And that stuff's not attached. If we shook this, it'll fall right back off. I'll have that original graphite electrode back. Right now it's just kind of covered in some stuff that came out of this copper chloride solution. Right, here at station number 6, we are going to be adding a little bit of hydrogen peroxide to our test tube, and then adding a very small scoop of this KMNO4 stuff that I've got here. So go ahead and write your observations of each of them. I'll get you a little bit closer look at that KMNO4. Not super interesting stuff. And we're going to get a super tiny scoop of that. And by super tiny, I mean we're using this itty bitty little spatula here and getting just that much of our potassium permanganate. We're going to go add that to our test tube. I'm just going to add a little bit more because half of that got stuck on the side. I was watching the video instead of the scoopula spatula. Stir that to get that mixing and reacting a little bit better. A little shake. Now I do mention in the instructions that this KMNO4 is a catalyst. And I say it's just a catalyst. And I use that phrasing to help remind you that catalysts are kind of the cheerleaders of our reaction. They help get it going, but they are not actually part of the reaction. So we shouldn't be including that KMNO4 anywhere in your balanced chemical equation. In fact, if we can finish reacting all that hydrogen peroxide away, you can kind of already see a little bit of that at the bottom. That KMNO4 powder is basically just settling at the bottom after that hydrogen peroxide has finished reacting. Come back and show you a picture of what this looks like when it's really done.